It is Wednesday, chapters 1 through 3. You will have your pencil, you will have your calculator. Notice I keep going back through this, so hopefully. Okay, you'll have your cheat sheet front and back. The last thing you're going to have is Friday, I'm going to be posting what's called a ZipGrader sheet, okay? And it's going to have a numeric code that is your code. Okay, that's you. Okay. And then it's going to have a password, okay? Now, to help me speed up my grading on this so I don't have to sit there assigning each person to their grade, I go ahead and let you put on your code. You'll have to also put your name as well, though. And what's going to happen is that will automatically connect all the grades. Now, what will happen is that sheet I'm going to put up there that has that code and a password, okay? And so you can then go to ZipGrader's website. I'll scan in all your sheets, and you'll be able to see your sheet. It'll show you which one's wrong, which one's right. It will also have the exam with the key, okay? And I'll do that whenever I get everybody having taken the exam. Now, will that be the same day? Almost certainly not, because there's a number of things that go on during an exam, right? First off, people miss the exam, and I have to get them to test. Second off, we also have accommodations that happen, and so I have to get that stuff done, and it's just not something that can be done all Wednesdays.
So that password and login to check that will be a full replacement for exams being handed back. Like instead of things being handed back, you just go online.
You'll get that. Yeah, and that will be available everywhere all the time, and you'll have I'll actually have 3 versions of the exam when you take the exam. I've had to do that since I started teaching here. I've just had so many people get caught cheating. So there'll be 3 versions of the exam. It'll automatically give you your version of the exam, and you'll have that available so you can improve your performance and understand it better. It's actually quite convenient. Yeah, works very nice. I pay a monthly fee for it, so it better be convenient for us. Okay. So in terms of missing the exam, okay, you'll have to come to the exam with that ZipGrader code. You'll want to put that on your cheat sheet. It's a very small number, and it's only numbers, 0 to 9. Okay?
Mm-hmm. Is there going to be a study guide?
There already is. Okay. Let me talk about missing, then I'll talk about studying. Okay? So if you miss the exam, okay, if you know you're going to miss the exam, you need to tell me as soon as possible. Okay? And we'll arrange a time for you to take the exam, and it may be before the exam starts, it may be after the exam starts. Okay? Now, you need to get that exam done before a week's over. Okay? If you contact me 2-3 weeks after the exam and Dr. Clausen, I'd like to take the exam now. No, it's already over, right? That's done. Okay? That's in the past. Concentrate on the next one. Okay? So within a week, you have to make up the exam. It's after a week, I'm releasing the exam versions, and it's over. You can't do it anymore. Okay? Yes, that may mean that you have to slightly inconvenience your schedule to stay here sometime when you and I are both free. Okay? My office hours, everybody's seen the Calendly office hours. You can just click on that. You need an hour to do the exam. If you want to do it in 30 minutes, that's fine too, but you're only going to get the 30 minutes. I got to go to class. Pick a time, schedule that time. There you go. That's your time to take the exam, okay? Okay. Have it automatic. Everything's, fast and easy to do. I know. Also pay for that service. A lot of stuff I pay for this. So okay, so everybody understands missing? Okay, fantastic. Okay, so in terms of study guide, okay, I don't do a traditional study guide because, number one, every study I've seen of using study guides has indicated they don't actually help at all. And so they actually hurt most people because they tend to sit there and try to do the study guide instead of anything else, which you'd actually be better off for, right? Yeah. So what I do is I've given you homeworks. They cover every single question type I could ask during the exam. Okay? And I've given you study guides at the end of every chapter's PowerPoints. So that instead of trying to cram that study guide I give you for the last week or something, you instead can work on the study guide as you go, right? Now, realistically, the study guide isn't super helpful. What's actually more helpful is the homeworks. Okay, the homeworks are everything. Realistically speaking, they take you through every type of problem in more detail and more difficult than I'm going to do on the exam. Okay, and so they will test you on every aspect. Now, could I give you, instead of doing like y equals x plus 1, could I give you y minus x minus 1 equals x? Oh, yeah, right? And that's the same problem, isn't it? Yeah. So keep that in mind when you're looking at these. Yeah, I can I can rearrange the problems, right? I can put different numbers there. I could put different elements. It's still the same problem, okay? So what I recommend actually is the best way to approach studying for this course is to sit down on those homeworks. And so if you've done the homeworks yourself, which hopefully everybody has, but I do recognize there is the ability to not have done the homework yourself. Okay, so I'm mentioning. If you've done the homeworks yourself, look for the ones that you struggled with, okay, that took you multiple attempts at, and then go back through and act like it's a test and try it again, okay? And kind of go back through each of the questions and go, do I know this off the top of my head? If you don't, try it again, because you can try the homeworks all over and over, and it'll always take your best grade. And so you can go back and redo all the homework questions that you had difficulty with or you're not sure about, and treat them like an exam question, just with your one page front and back, nothing else, no book, no nothing, just your calculator. And so if you go through and do that, you're going to be really well prepared for the exam, because honestly, those are harder than the exam questions. I also have a review. The review, without being like a 10-hour thing, right? I didn't want to make it a 10-hour thing. It's worth some bonus points, worth doing. Altogether, all the reviews will give you enough that if you get a 50% on exam, you'll have gotten 100%. Okay, it's worth half an exam altogether if you do all those reviews and get max points. Okay, you can do them multiple times. Whenever you start it, it'll tell you how many attempts you have remaining. Okay,
So is it like practice test?
it is.
Okay.
Yep, it's like a long practice test. Yeah. It's on Pearson, yes. Yeah. And so I've done my best to sort of make it like a practice test. Do at least one of the attempts like you're doing a practice test, like test environment sort of thing. And then you can do it again to get the grade if you want. But yeah, it's like a 2-hour version of the exam. Yeah. And it randomizes the questions, but within banks. So like I have a selection of questions for each sort of category that you could get. Okay.
So you're taking the best score.
And best score.
Mm-hmm.
Yep. Whatever your best score is. So, and it's a really, really good measure for you of like how prepared am I. Okay. But only if you take it like an exam. If you take it not like an exam, it's not going to do a lot for you for that. Did that make sense? Yeah. Okay. There is the study guides at the end of each of the PowerPoints. Realistically speaking, though, I have done everything in terms of study guides over my 15 years of teaching. And I've seen every type of study guide done over that time. And I have not seen a single example where study guide did better than non-study guide overall in course grades. So, and I've seen studies on it, and it just is, if I'm going to give you a study guide, I'm going to give it to you so you can start early and not do it all at once.
So the study guides are a good representation of what the exam
Yeah.
questions will.
They're a good representation of all the materials that are covered in the chapter and what the important topics and concepts are. But the homework's even better representation. So, and it tests you on it, right?
Mhm.
So if you have trouble with a problem on the homework, that's what you need to concentrate on. The study guide would be, if I was to rank priorities, it would probably be somewhere below half. Just because they don't really help as much as people think.
Mhm.
It's just a convenient thing to focus on, and sometimes you end up wasting focus. The homeworks, I've structured everything so you actually get the full smorgasbord of learning.
Mhm.
Yeah. And maybe too much. Okay. Anybody have any questions at all? Yeah, I'm going to have to make you chant this real quick because I get some really interesting questions these days. If you see anybody that's confused nearby to you and seems like they don't know what's going on, please talk to them because like there is just no common set of knowledge anymore. Okay? I get asked some really interesting questions like one of the questions I've been asked in the last year is, Dr. Clausen, will the exam be at the same time as the normal class? Yes, it'll be at the same time as normal class. It's during the, next week's class, right? Do we still meet at the same time? Yes, after that, we still meet at the same time, okay? So, yes. So next week, what time? 2 p.m. Very good. What day? Wednesday. And what all do you have to bring? Pencil, calculator, cheat sheet, 1 page front and back. Don't play games. And your ZipGrader code, right? Okay. Are we good? Everybody looked like they were with me?
I assume once we're done with the exam, we just are good to go.
Yeah. Oh, yes, most definitely. Yeah, if you completed early, you're...
Where's the code at?
It's not up yet.
Okay.
Yeah, so where the code will be is you're going to see that I'll have, on exam 1, you're going to see that I'll post responses to you, and you're going to go, what the hell is he responding to? I haven't done it in exam 1 yet. Okay? And what the responses are is they're going to be little PDFs with a link to the ZipGrader and your code and your password. Okay? And you'll be able to access the ZipGrader from that. It actually is nicer if you just download it and keep it. I will warn you that Canvas app is really bizarre and does not let you open like attached documents. So you will have to use the browser. Okay.
Will it be the same like code for every test?
It will be. Yep. Same code, same place. You'll see all the exams lined up there eventually. My phone's going off. Over there. Okay. So let's go ahead and start the lecture. We're going to go and get through the rest of the materials. What you'll notice is we will again be covering Chapter 3 today, and then we'll finish Chapter 3 next time. You should go ahead and start the homework before next time, because we'll have covered most of the material. Chapter 4 we will actually start next time as well, okay? And so Chapter 4 will not be on the exam. I always start the next chapter, okay? That way you guys have a little bit of extra time before the next exam, okay? Okay, so let's talk about, we were talking about the predicting charges, right? Whenever we're talking about an ionic compound, it's always going to have a net charge of 0. The easiest one to predict charges for like the metal from is going to be the anion, okay? Because it's a very limited selection and they're all main group elements, right? And so you know the charge of the anion with a great deal of certainty, okay? And so, for example, oxygen has what sort of charge? It's 2 steps from a noble, so that is 2 minus, right? Fluorine would have a 1 minus because it's 1 step from a noble, isn't it? Okay? Now, when we name ionic compounds, there's going to be 3 different sort of brackets that we need to name here, different groups that have slightly different naming, okay? What we're going to have is the first one. This is going to be a very simple ionic compound, and it's going to be things that are going to be our main group elements, okay? And so, for example, groups 1, 2, 3 are going to be our metals for these. And then the groups over in the 4, 5, 6, 7 are going to be our nonmetals for these. Okay? And we're going to see things like sodium chloride. Okay? Notice that used to be sodium ion, right? We're going to omit ion. So we're going to put the metal, and then we're going to put our non-metal's name. Okay. So we have sodium chloride. We could have magnesium bromide. We could have aluminum oxide. Okay. Those would all be examples of names for these, properly named. Okay, so for the transition metals, well, we have a little detail we need to add to these now, right? These aren't so simple anymore. Those dang transition metals can have multiple charges, can't they? And so we need to list the charge. Okay? So for example, copper oxide, well, there could be a copper 1 oxide, there's a copper 2 oxide, both are options. Okay? They have different colors, they have slightly different properties to them. Like, they're different compounds, okay? In fact, if you look at the patina on copper, that's why it has that sort of beautiful, like, green blues that go everywhere. Yeah. Those are two of the forms of copper oxide, okay? There's also more forms, too. There are nitrogen and all sorts of stuff, but that's why patina is really kind of beautiful. So copper 2 oxide is this one. The 2 Roman numeral there means it has a 2+ charge, right? Okay. And that's the formula for it right there. Notice that I've had the 1+ charge. This would be Cu2O, wouldn't it? Would have had a different formula. Okay. Polyatomic ions. If a polyatomic ion is present, then it really doesn't do a lot to the naming, but you do need to know your polyatomic ions. Okay? So the polyatomic ion is going to be unchanged in the name of the compound. And so, for example, this right here is the polyatomic ion right there, phosphate, right? And so we're going to have calcium phosphate. Okay? That's it. That's all the naming for ionic compounds. Right? Once you have your polyatomics, mostly memorized, these are going to become pretty trivial pretty quick. Okay, you'll do them real fast after a while. Keep in mind, this is partially a language class, right? I would call it about 40% language class. Okay? You're learning this language. Now, nonmetals will combine by sharing valence electrons to achieve what your book likes to call the octet. I prefer calling it the noble-like configuration, right? And so they're going to combine their valence electrons. So instead of each one giving one or losing one, they're going to combine them so they both have those 8 electrons that they would want. Okay? Now, this is going to form what's called a covalent bond, because when you put the electrons between the two, they're both going to be attracted, and so you actually get a connection between them. And so that's the covalent bond. It's a pair of electrons that are pulling these two atoms together. Okay? And so you get your covalent bond. This means that they're sharing those electrons. The valence electrons in the bond are going to belong to both atoms, and so you're going to count them towards both atoms having their quote-unquote octet or noble-like configuration, right? Now, when the atoms share those electrons, this is going to result in what's called a covalent compound. Okay, notice the naming, covalent bond, covalent compound. Then it tells you they're sharing the electrons, okay? So, the smallest or fundamental unit of a covalent compound, this is going to be a molecule. Okay, this is where you get molecules. They're nice, discrete units. Notice that if it's not covalently bonded, then it's not a covalent compound. It's not the same molecule as it. Okay? So, ionic compounds, we could only do formulas. We do the lowest common denominator formula. And so, if we had a huge salt crystal, okay? You can get really big salt crystals. Have people seen that you can make big ones the size of apples and stuff? And they make those things for horses and animals that like the salt, right? And so you can get very big salt crystals. That's going to have 10 to the 30 sodium atoms. They're all ionically bonded together. Okay? So if you were to sit there and try to name all of these so they're not just the lowest number possible, you'd get a big one, 10 to the 30, right? And so you'd have to be Na 10 to the 30, Cl 10 to the 30, right? And then you get a smaller one, and it's going to be 10 to the 20. So Na 10 to the 20, Cl 10 to the 20. And then you get the little tiny crystal, and now it's 10 to a billion. It's Na billion, Cl billion, and you'd have different names for every single salt crystal you make, right? Because which one is the pair? You don't know. So we don't name those, we just name them based on their common denominator formula, okay? There's a 1-to-1 ratio for the sodium and chloride and table salt. And so they're all NaCl, okay? When we talk about something that's a molecule that has covalent compounds, so it's going to be like water, right? H2O or CO2. And so one CO2 is separate from another, isn't it? Okay, one water is separate from another. Okay, they're not covalently bonded together. Right. Does anybody know if you've ever seen a molecule with your eyes, by the way? No? Who here thinks you have? One? Cool. Yeah. Who here thinks you have not? Ooh, the overwhelming majority. Okay, a lot of you kind of didn't answer because many of you may have figured that I was kind of setting you up a little bit, right? But it's kind of neat. So you're actually seeing molecules right now that you can see with your eyes, okay? And those are actually, I have less of them now than I used to have when I was 20. And that's hair, right? Those are a type of polymer. And so polymers are just very, very long molecules that are covalently linked all throughout. Your plastic folder, for example, that's another polymer. Your plastic chairs are another polymer. And so those are actually molecules for the whole piece, okay? Because they're all covalently bonded together. We have special language for them that we won't go into in this course. But if you're ever interested, you can take some more chemistry and talk about it, or you can just come in. We can talk about it. No, I'm not going to reject you learning new things. Come on. That's why I work for Thirdwood. I normally get paid. Okay. So when we name ionic compounds, your number of covalent bonds that an atom will form is going to equal the number of electrons necessary to complete its octet. The electron dot symbols were actually developed by a chemist named G.N. Lewis. This is actually to show how many electrons will be involved in things like covalent bonding. And so what you're going to do is you'll put the symbol of that atom, and then you're going to put the valence electrons around it as dots. Now, the electron dot symbol for any atom is again going to be the valence electrons put around it. What you do when you do this is, for example, we have Cl. If we were to write Cl and we didn't understand exactly where we're going right off the bat, you're going to go like this. You're going to put one dot on each side. Okay? And then that's 4. We need 7. And so we go ahead and put another dot every place until we're done. Okay? And so you're left with one unpaired one. Okay. And that's going to be your chlorine. Right? That's your dot symbol for chlorine. If you were to do carbon, it would just be one on each side, wouldn't it? Okay. Once you get some practice, you'll shortcut it because you'll know, 1 unpaired for 7. If you have 6, you need 2 unpaired. Yeah. So. Okay, so whenever you do these, what's going to happen is the covalent compounds are going to be the nonmetal with the nonmetal. These are going to involve sharing electrons. So they're going to share electrons. That's going to form what's called a bonding pair. Okay. We typically just call that a bond. It's going to be a pair of electrons that will form that covalent bond, right? Okay. Now, we're going to do this with a line, okay? So you're going to draw on a line. That's the bonding pair right there, okay? That represents a bond, right? This is another symbols that do work. Scientists do use them. They work great when you're typing them. And that is you put a pair of electrons between the 2 atoms, okay? Do not use this when you're drawing this on a page. You will mess yourself up so much you don't know where you are, okay? Because think about it, right? You have a pencil usually that you're going to be using, maybe a pen, and you got your page, and look at your pages. They have like little flakes in them that look like little marks, right? So you're going to be in a hurry, and you're gonna go, and they're gonna be. This is gonna look just like the flake over here in your page, and the one over here in your page, right? And so now, what is that? What the hell is it, right? I don't know. Has 4 electrons? What the hell, Dr. Clausen? It's literally what you're going to go up to me. You're going to be like, Dr. Clausen, I was taking notes, and I got these notes of what you were saying, and then I don't know what this is. And I'm going to go, what the hell is that? Why does it have 4 dots? And you're going to go, I don't know. And then we're going to look back in the notes, and we're going to be like, when was the notes? Okay, what was ahead of it? What was behind it? We're going to find it, and we're going to find out this is what you meant to put. Okay? You tried to do a bonding pair. And it's going to be a whole 30 minutes to an hour thing, okay? So I refuse. You refuse. You want to know what you actually put, okay? So you're not going to put the dots. You are going to draw in the line, okay? You can't mistake that for anything else. Okay? And I'll be honest, even my own writing, unless you notice I like draw around and then fill in, because I have to be very intentional. Yeah. Now, in terms of like putting these in typing, this is very convenient, because it's actually easier to just go, colon, than it is to do something else, isn't it? Yeah. So it works really nice in typing. Okay. Looks beautiful, right? My God. Nice coloring. And ooh, But it works terrible on your notebooks, okay? So this is a bonding pair. It's a pair of electrons that are being shared in a covalent bond. This right here is what's called a lone pair, okay? So it's a pair of electrons that are off by itself on one atom. They're not shared between the 2 atoms, okay? They're not involved in bonding. So let's ignore carbon for a bit on these other patterns we're going to discuss, because carbon's a little bit of an outlier and does some fun, interesting, cool stuff, okay? It's also why everything's made out of carbon, because it does fun, interesting, cool stuff, right? So if we ignore those carbons, what we're going to see is here's hydrogen. That is what carbon looks like, but we're going to kind of ignore the results of that. And then right here's the nitrogen, oxygen, and fluorine, okay? And so what we can see is most of these just have like 1 dot on the side there that's open. And so they tend to make 1 bond in each of those places, because each bond typically has 1 electron from each of the atoms. And so, this can give 1 electron there, and it can receive 1 electron. That makes a bond, okay? And so you can kind of see their typical bonding patterns from that. Now, fluorine, chlorine, all the halogens make the same sort of bonding patterns typically, which is 1 bond. Okay? If you're in group 6 there, you're going to typically make 2 bonds. Okay? Now, notice there's actually an easier, faster way to say the same thing. Just count over to your nearest noble, and that's the number of bonds you would want to make, right? Oxygen's 2 away from the nearest noble, and so that's wants to make 2 bonds. If we look at nitrogen, that's 3 away from your nearest noble, and so that's going to want to make 3 bonds. Okay? Because it wants to gain 3 electrons. Every bond shares 1 extra electron, doesn't it? So it gains 1 electron.
So would phosphorus have the same as?
Typically, yes. Yep. For the most part, phosphorus is going to have the same bonding type as nitrogen, okay? The group 3 and lower, though, because they can take on more electrons than 8, can also do some other crazy stuff, okay? For the most part, that's or another way of saying, like, they'll have the same sets of compounds as you'd see for nitrogen. They'll just have some other stuff they can make too. Yeah. Actually, phosphorus can make a whole range of like explosive, crazy gases. They can do all sorts of weird stuff.
And that, like white phosphorus? Isn't that like a
Yeah.
war crime?
Yeah,
Supposed
it
to-
is. Yeah. It's actually really easy to make too.
Because it's like sticky, right?
Yes. Yeah, it burns really hot. It's very sticky. Yeah, and it doesn't go out with water. So you end up burning a whole lot of people alive. Yeah. And it spreads to everything because people run around. I'm on fire, and then it sticks to everything else too. So it's just. Actually, I knew a lab. Phosphorus labs are really funny because they don't build like nice buildings. So if you ever saw a phosphorus lab, the labs are either built individual like shacks, or they're built so they can drop out of the main building. And what you do is you build the building, and you'll see lines of them. You'll see them from the highway oftentimes. They're either silicon or phosphorus labs, and they make silanes in them. And what they are, you'll see like a burnt out wreck. Then you'll see one or two of them. They're like active, and then you'll see one of them that doesn't have the stuff plugged into it yet. It's just on the side. Because they're burning them down, running out of the buildings and going to the next one. I used to know somebody that worked with that. Yeah. I actually worked with silanes for a while. They blew up with it almost blew my hand off. It somebody let it go to the trap, and then they let the trap heat up and release the gas into the atmosphere, and it blew. Yeah. So single bonds. For example, if we look at carbon typically wants 4 covalent bonds. It's 4 away from the nearest noble. And so it can make 4 single bonds, and that would give it 4 bonds. Okay. It could make a double bond and 2 single bonds, and that would again give it 4, right? It could make 2 doubles. It can also make what's called a triple bond and 1 single bond. Okay. And that would again give it 4. Any combination of single, double, and triple bonds can be done as long as it gives it the 4 bonds. Okay. Your book does this entire table and spends like 10 pages on it. And it's just kind of silly because I've just summed up the entire thing and we're done. Okay. Done. 2 things to memorize. There you go. Congratulations. I don't know why. Apparently your book doesn't think you can count to 4. I don't know. But I think you can count if that helps. So you got your different combinations you can do here. If you want to know why you can't do a quad bond, a 4 bond, there's 3 dimensions in space. And so when you make a single bond, you have direct overlap, and the 2 electrons will be between the 2 atoms. Okay? And so you're taking up that space with the first 2. Right? The second 2, like if you're next to each other, right? You could directly hand her something, right? The other way you could do it is, let's say her computer's in the way, you can hand it around the 2 sides, right? That would be like your double bond. Okay? It's around the 2 sides. And that's how they're sharing the electrons. They're doing it around the 2 sides, around that single bond, right? The first bond. And then there's one other dimension set that you could do this over. You could hand it over the top, right? And that'd be your triple bonds. Okay? But once we've filled all that space up, you're blocked, aren't you? There's not another dimension to go in. Okay? And so there's no 4 bond. Right? Because there's just not another space for it. All right. Now, remember, you're going to get everything to be noble like. Okay? And so, if you look at your periodic table, count the number over to your nearest noble, right? And that's how many bonds you're going to want to make for everything. So, for example, nitrogen wants 3 bonds, right? It can make any combination of single, double, triple bonds as long as you give it 3 bonds. Okay? Can you give it 1 single and 3 and a triple? Nitrogen. That's 4. Is carbon, sure. Not nitrogen. Nitrogen could get a triple. You could do a double and a single. 3 singles. Sure. Okay. Everybody okay with that? Yeah, I think the way I just told you is usually the better way. It's It's actually fairly simple once you get used to it. Let's talk about molecular formulas. They're a bit different than the formula for an inorganic compound or ionic compound. Okay, so molecular formulas are going to have covalent compounds. It's going to identify all components of your molecule, and it has to actually have the full number of atoms in it. Okay, and so, for example, glucose has C6H12O6. Okay, so if you have a glucose, it's going to have 6 carbon atoms, 12 hydrogen atoms, 6 oxygen atoms, no more, no less, right? Now, for the ionic compounds, you'd reduce that to the lowest common denominator, don't you? Okay. However, if you do that for these, you're going to have a huge problem. You will not have glucose anymore. You will actually have a compound that is not very common in your body. Okay, you would not want to eat it. It's not. It's definitely not glucose. Okay. Probably the easiest example though is actually OH versus H2O2. And so H2O2, that's going to be hydrogen peroxide, like you get for bleaching things. OH, which is just one of each, that's actually the most common oxidizing agent in the atmosphere. It's generated whenever rain hits rocks. It's generated. By the way, that's why you can like bleach jeans in a stream, if you're wondering. Stonewash. That's how that works. Is water actually generates OH whenever it hits something hard. And that's actually the most common oxidizing agent, not the oxygen. Yeah. Okay. And so, again, don't reduce them to the lowest whole numbers. The formulas, however, does that tell you how that's bonded together, really? Yeah, you have no idea, right? And it doesn't really tell you anything about, like, what does it look like in three-dimensional space, does it? It's kind of like listing the parts of a human, or the parts of, like, a machine, or the parts in a recipe, right? It doesn't really tell you what the recipe actually is. Like, I have sugar, flour, water, right? There's a lot of different recipes it could be, right? It could be types of bread, it could be cakes, it could be cookies, it could be... And if I don't feel like one of those, then I might be out of luck, right? So you need to transmit more information sometimes. And yeah, this is really condensed, but it doesn't transmit a lot of information, does it? Now, the more information you transmit, the more you have to write. Okay? And so that's why we have these different stages of formulas, okay, that we're going to talk about. That was your molecular formula. CH4, this is methane, as in like natural gas that you light up and burn at your house. This is going to have all nonmetals. It's a covalent compound. You're going to have carbon here. It's going to want to make 4 bonds. And so those hydrogens are going to each make 1 bond, right? And so they're all going to be arranged around the carbon, each making 1 bond. Okay? Okay. Now I'm going to quickly teach you the easy, fast method to do this. Then we'll go on to the slower, but always works method, even if you don't know what the hell you're doing. So the fast method, but you kind of need to know what's happening in life in this class, is that I've told you bonding patterns, right? So like oxygen wants to make 2 bonds, right? Carbon wants to make 4 bonds. Hydrogen wants to make 1 bond, right? And so what you always do is you take the thing that wants to make the most bonds, that goes in the middle, okay? And so carbon goes in the middle in this case, right? And then the things that wants to make less bonds, well, it can't branch out as much, can it? So it's not going to usually be in the middle. And so what you do is then hydrogens each want 1, and so you fill it in with hydrogens, so you get your 4 bonds, right? Okay, so let's try something slightly more difficult. CH2. Okay. So again, carbon goes in the middle, right? Okay. Hydrogens have to go off that carbon. That's the most likely candidate. Okay. And they each make 1 bond each. How many bonds does oxygen want? 2. And so I make 2 bonds to the oxygen. And there you go, right?
Why wouldn't it be up? Oh, never mind.
Yeah.
I,
Can't make the...
yeah.
Now, if I had an extra hydrogen, I don't have used all my hydrogens yet, have I? But there is a way that I can assemble this so all my bonds get made. And that's by putting a hydrogen here, right? Okay. And then I need one more here, right?
I have a question. It just may have been like what you said ask, but I'm just confused why like the two hydrogens can't connect like on the furthest right side.
So let's say you did this. Each of those hydrogen now has one bond, yeah. But that's no longer the same molecule, is it? That would be H2, CH2, right? And they're totally different molecules.
So even if you connected them like within that molecule, it still wouldn't.
Where do you want to connect it? Right here?
Yeah, I was meaning like the furthest right side.
What do you mean?
Like right there, yeah.
Okay.
Does that work?
That has two bonds going to hydrogen. And so hydrogen can only make one bond. Does that make sense? And so, yeah, once you did that, you go, oh, whoa, 2 bonds. Yeah, that's not okay. And then you'd have to. Is that making some more sense? Right. Okay. Now I'm going to go ahead and go through the long way to do this. This is, once you get kind of comfortable with these, that is by far and away the faster method. And you'll be able to get through 90-something% of these examples real fast just using bonding patterns, okay? Like, honestly speaking, there's very few of these I would give you that can't be figured out with bonding patterns. But I'm going to not do it the way your book says because your book's method doesn't always work. And if I'm going to teach you a long method to use, I'm going to make sure it always works. Okay? Which is just silly, right? Okay. So, I do like this book for a number of reasons, but it's definitely written by a nurse, not by a chemist. Like, it's really great medical stuff. The chemistry stuff is a little. Okay. So, when I look up here, I have CH2O, okay? And so I've been given this, and what I want to do is I want to figure out what the Lewis structure for this is. I'm going to do something simple that you've already seen before, and then we'll go to something more complicated that you haven't seen, okay? Because I want you to start with something a little simpler, that you know what we're getting. So the first thing you're going to do is you're going to calculate how many electrons do I have to play with, okay? How many electrons do I have to use? That's the number of valence electrons. So carbon is going to have how many valence electrons? 4. Group 4, right? Hydrogen has 1 valence electron, right? Group 1. There's 2 hydrogens, so there's 2 of those valence electrons in this molecule. Now, oxygen is group 6, and so it has 6 valence electrons. Okay. Everybody getting that so far? Yeah, I'm just counting up how many electrons do I have to use, right? Because all those electrons, they have to be used, and no more electrons can be used. I don't have any more. Okay? Okay. And so that is 12 altogether. So again, you're going to take the thing that needs the most bonding, you're going to put that in there, okay? The thing that needs the most electrons before it's a noble gas. It's noble gas. Okay, and I have my carbon in the middle, okay? Now, because this is a molecule, and it's written like this, tells me it's a molecule, I have to connect all of these with at least one bond, don't I? It's not bonded together, it's not a molecule. Okay? And so I'm going to put one bond to everything that's going to surround this. Okay? And so now I have one bond to each of these. I've used up 2 electrons for every bond. And so I'm going to use up 6 electrons in that, leaving me with 6. Okay? Next thing I'm going to do here is I have 6 electrons I have to use, don't I? And so I'm going to go around the outside, okay? I'm not going to touch the carbon in the middle yet. Never touch the middle until the end. Okay? Because the middle is where you are going to do the next step. Okay? So this hydrogen right here, does this have its full Nobel configuration? Yeah. Yeah, it has 2 electrons. How about that hydrogen? Yeah. So I can't add any more to those, can I? How about the oxygen? No. Now, it's very important whenever you do this that you use something you can erase with. Because if you can't erase, you're going to end up with a big mess here. Okay. So I add 6 electrons to this, right? And that would give the full electron configuration of 8. I can add 6 electrons because I had 6 electrons here, right? And so now I've used up all my electrons, okay? Okay, all electrons are accounted for. If I had any extra electrons, they would go to the center, okay? So if I had an extra 2 electrons, I'd put those here, right? But I don't. All right, so the next step I'm going to do is I'm going to go, do I have everything with a full octet? Do I have it at Nobel configurations? This one, yes. What's that one? I'm short, aren't I? So what I'm going to do is I'm going to pull one of these lone pairs into that bond. Okay? And that will share that pair of electron with that carbon. Right? And so now I have full electron configurations for everything going. And see, that's kind of the secret sauce of this. I'm using basic mathematical accounting, right? And if I follow my steps, I will always generate all my double bonds, triple bonds, everything. Okay? And I'll always get them in essentially the correct places. Okay, so let's try the next one. We're going to do CO2 real quick. In case you want more examples of me taking you through these and you forgot the rules or didn't get them out in notes or whatever.
So when you put the point underneath,
Mhm.
then switch to the 2.6.
So you would have still not had. So I'm at there, okay? Okay. If I went like this, I'd have 4 here, but I would not have 4 pairs here, right? And so I got to share them to get full octets on both done. Yep. And that's one of the reasons you always want to fill this one in first. Is because if you run out of electrons, then you know you need to share stuff. It makes life a little easier. If you start with the middle, then you're never quite sure where you need to share the bonds, and you have to figure that out. Okay. So CO2, we have 4 plus 2 times 6, right? Everybody okay with that? And so that is 16 electrons total. Okay. Everybody good? 4 valence electrons, 6 for the oxygens, there's 2 of them. 12 plus 4, 16. Okay, what goes in the middle? Very good. Okay, how do I surround it? Very good. Okay. You'll notice I'm like putting them the furthest distance they can go from each other. That's actually going to become important later on, but we haven't covered that. Okay. Okay, so I've used up 4 electrons so far. I have 12 remaining, right? And so now I do what? Yeah, you're shortcutting it. If you do that, you'll have to always remove bonds and stuff to generate lone pairs. If you start by filling it in with the lone pairs first, then you don't have to go back and forth and try to figure out how to solve this. You'll always be able to just go through the steps and get right every time. But yes, you could. Yeah, because that is exactly what's going to happen. So I filled it in with my 6, 6, which is my 12. And so now I see that I'm short 2 pairs of bonds. And so I'm going to take 2 from this one. Now, whenever you do this, you always want to go ahead and distribute this as much as possible, okay? Try not to take it all from one if you can help it, okay? And so I take 2 from here, and that's my carbon dioxide right there, okay? Okay. Anybody have any questions there? Note that you'll still get these right even if you have an extra octet. Okay, an extra octet meaning you have more names, right? Just keep in mind the thing that will be in the middle then is always going to have to be something that's period 3 or less. Okay, lower than period 3. Period 3 or lower. Okay, let's go ahead.
How do we know like the overall state of the model? So, like, for example, if you have like a
We'll get to it. Let me do the naming first, though, okay? Because you gotta be able to talk the talk before and walk the walk, right? Yeah, but it's called Vesper. It'll be nice. Okay. And so for naming covalent compounds, they have special rules for naming them. We're going to start with naming binary compounds, okay? Binary meaning only 2 different things that we're naming, okay? That would be an example of a binary compound. We have a carbon, oxygen. So binary compounds are going to have 2 elements. We'll name the first element in our formula. In this case, we have carbon, right? You already know the name for this one because you've said it many, many times in your life. And so the next thing we're going to do is we're going to change the ending for the second element. And so normally that would have been carbon oxygen, right? So instead it's carbon oxide, isn't it? Okay. Now you're going to designate the number of each element present as using one of the Greek prefixes. I'll have a list of the Greek prefixes in the next slide, but I want to talk about some exceptions real quick because you can get confused about it, okay? And I got a little story I want to say before I give you all the information. It'll be more fun. So again, indicating the number of each element that's present is very important because your nonmetals can combine with each other in multiple ways. You actually know this because you've heard of carbon monoxide, right? And carbon dioxide. Okay? Guess what that is? Like, yeah, 1 and 2, right? Monocycle, cycle, monocle, 1. 2, bi, right? Di, 2. And so that's carbon dioxide. If we had only 1 oxygen, that would have been carbon monoxide. Okay? Okay. And so some compounds like water, ammonia, and nitrous oxide, these are actually known by traditional names. They're just common parlance. And so people don't tend to name them according to the naming rules. You can name them according to the naming rules. People will just look at you really weird. Okay? Okay. Now, my funny story actually involves, I'm going to give you a little example, and I'm going to tell you what my students and other students have done with it, okay? So I'm going to play it like I'm trying to fool you all, just like my students or other people's students have done, okay? And it's kind of a fun little game you can play where you mess with people that don't know chemistry, right? And unfortunately, people do this for not fun reasons as well. But, okay, so I'm going to tell you guys about a drug that is 2/3 of the global warming effect. Okay? It causes 2/3 of the global warming that is being done by humanity right now. Okay? It is the leading cause of property damage on the entire planet. By far and away, nothing comes even close. All other causes cause less property damage than this. It is 100% addictive. Humanity has never made anything nearly as addictive as this compound, this drug. Okay? People use this all around the world, and they have their lives ruined by this every year. More people die from consuming this compound than every other compound combined. Okay? This compound is responsible for more human death throughout history than nearly any other cause. There's only 2 other causes that have killed more people. Okay? And this compound's name is dihydrogen monoxide. Okay? This horrific plague upon humanity. Are you all with me? Are we going to go march on Congress and get that damn thing banned? Did anybody catch on to what I just told you was the cause? Yeah. Di2, right? Hydrogen. Monoxide. Mon 1. So H2O, water. every single fact I told you was true, wasn't it? More people drown from water than any other overdose cause.
I mean, I wouldn't say it's man-made.
We make water all the time. Yes, that's actually how you respirate. So one of the things you make when you respirate is water. So you make water all the time. And it is 2/3 of global warming is actually caused by dihydrogen monoxide water. Only less than 1/3 is caused by CO2. Every single thing I told you was 100% true. So the funny experiences of this is that this was done to Arizona State Senate once by a group of students, and they actually tried to designate money and ban dihydrogen monoxide in Arizona. Also done by my students on Facebook once, and so they were messing with people, and the people who are in the know were making it bigger and bigger, and they're playing around with it. And one of my students actually ended up having his mother yell at him and refused to speak to him for 2 weeks because he was laughing about it. She thought, this is a horrible substance. Why are we allowing this to be a thing, right? And he was having fun with, haha, they're trying to ban water. Like, this has repeatedly had like 10,000 person petitions, which I find really funny in the age of the internet, especially on Facebook, where you could just right click and search, right? But whatever. This right here is the Greek prefixes. Mono, like monocle 1, di 2, like bi, they're the same sort of thing. Tricycle 3, tetra, like tetris 4, tetris 4 sides. Penta, like pentagon 5. Hexa, like hex wrench 6. Hepta, like heptagon 7. If you needed more, you can go up the octagon, etc. You almost never need more than 7, though, to be honest. It gets pretty rare at that point, and most people don't even bother. It has like actual names for compounds at that point. Okay, so if we're looking at naming any compounds, this is the flow chart to sort of help you out and direct your efforts. Okay, so if it has a metal and a non-metal, it's likely ionic. Okay, and so if it's an ionic compound, then the next thing you want to ask yourself is the metal in groups 1A, 2A, or 3A? Okay? If the metal's in group 1A, 2A, 3A, then you don't need any Roman numerals, you don't need Greek prefixes. Very easy, right? Potassium chloride, sodium chloride. Congratulations. Okay? If the metal is not in those groups, then you're probably going to need Roman numerals because they're going to have variable charges. Okay? That's where you start encountering a bit more complexity. You don't need the Greek prefixes yet because you only need those when you have covalent compounds. Covalent compounds are going to be where you have a non-metal and non-metal only. Okay? And so you're going to make covalent compounds then. In that case, you don't need the Roman numerals, but you do need the Greek prefixes. Okay? And so you're going to have your monoxides, dioxides, trioxides, etc. Okay? Not just oxides, obviously. Okay, so let's talk a bit about numbers in chemistry, okay? So these amounts of stuff, like even a few grams of a substance in chemistry, you're talking about billions times a billion atoms, okay? You're talking about just ridiculously large numbers, right? So chemists have designed a unit, it's called the mole, and this is used to relate the mass of an element to the grams of the number of atoms it contains. Okay? And we've done a really clever trick. We've taken that number that's called the mole, and that makes those numbers up there on the periodic table that were AMUs. Well, that's actually the mass in grams for 1 mole of that substance as well. Okay, so it's made the periodic table really, really useful, right? Because if you get a mole of that, you get that many grams. Now, the best way to think of a mole, it's like having a pack of something, okay? So it's like having a dozen eggs, right? So if I say I have a dozen eggs, you know 12, right? If I say I have 2 dozen, you know 2 times 12, 24, right? and so on and so forth from that. Okay? And so all a mole is a package of something. Typically, it's going to be atoms or molecules. Could be particles, though. It could be electrons. It could be anything, really. Okay? Because it's just like saying dozen, right? I can say I have a dozen particles. It means I have 12, right? Not a problem. Okay? You could have a mole of eggs. It'd be a hell of a lot of eggs, but you could have a mole of eggs. All right. So again, if I have a dozen eggs, right? Each egg is 60 grams. Then if I say I have, how many grams is that? What do I do? How many grams is a dozen eggs? Well, I take 12 times 60, right? And that gives me my grams, doesn't it? Okay, and I can do that math pretty easy. Now, I've just proven to you that all this stuff with moles is going to be very easy for you. And then you're going to say, Dr. Clausen's such a liar. Okay, and so if I have a mole of carbon-12, I have 12 grams. Okay, if I have a mole of carbon-13, I have 13 grams. Okay, mole of oxygen, 16 grams. Okay. Now, the 1 mole of any element is going to have what's called a molar mass, literally mole mass, right? And it's going to be in grams numerically, okay? And it's going to be represented on the periodic table by that number up there. Okay, that'll be your grams of 1 mole of that. Now, the molar mass of 1 mole is substance is going to be both the single atom AMU and the mass of a mole, okay? Now, this is how much a mole is. It's a kind of weird number because the numbers on the periodic table had to be the same things, right? So it's going to be represented in scientific notation, and this number here, 6.02 times 10 to the 23rd. Okay. By the way, mole day is 1023. Okay. And so this is this written out. It's a very, very large number, right? Obviously. It's billion times 100,000 or so? Very, very large number. Yeah. Huge amount of stuff. That is 1 mole of carbon. You know those weighing boats in lab? Are like that big? Yeah. It's 12 grams. It's not even a full coal that you'd burn at your fire, right? It's not much. But again, that's 10 to the 23rd atoms. Okay, this is known as Avogadro's number. I will stop now. Sorry. You all have a great day, and I'll see you next time. We'll finish this material. We'll get into what these look like in terms of shape, and it'll be glorious.
I was gonna say I came in late, and I still be counted as